Hello and welcome to FSharp.TV. This video is about benchmarking some shuffle functions, and feel free to follow along. I'll do it at a pace that you can also code alongside me. My name is Mark Gray. I'm one of the co-founders of FSharp.TV along with Brice Fernandez, and we've also partnered up with Henrik Felt from Logibit. He runs a company that does artificial intelligence and F# for making build taking easier. You can find us at FSharp.TV, and if you want to find more information about what we're doing, or you want to find some more content that can be interesting to help you learn, follow the link at the bottom of this slide, which is the Gazette page. You can sign up here and you can get information on a regular basis from FSharp.TV and from the wider F# community. The symbol on the right is the Xamarin logo. That's because Xamarin are our partners and they've contributed quite a lot to enable us to produce some fantastic courses. Let's get started. The reason why I want to do this video is because I'm doing the course on F# in the workplace. You can find a link at the bottom of this page. And as part of this course, we're going through some algorithms to sort a deck of cards. So we're going to implement algorithms. We're building up a domain as part of this course. And I was talking to my friend Dave Craft at CraftyFella, the link at the top, which is his Twitter handle. He felt that the thing that I was talking about was a rather good idea, and the thing I was talking about was comparing shuffle functions and enabling us to benchmark them. I told him about a conversation I'd had with one of my advisors. As a student, he decided to tell me that that's what he would like to hear. So I want to share this video now so we can start gaining further insight into how we write shuffling algorithms as developers and what considerations we should be careful of when we're writing our functions, and the big O notation and the considerations that brings with it also. So like I said, this session is to help supplement the course, although it is standalone, but it's to supplement the course for the link that you can see below. So if you like what you see in this video, then you can go to the course and get a bit more information there. So in this session, what are we going to be doing? Well, we're going to begin by developing some shuffling functions using F#. We'll write the code to benchmark each function, and then we're going to talk about some of the features that the functions have. Some of these functions are deliberately bad, and I'll point out the bad parts of the algorithms as we go along. But hopefully I'm going to do it at a speed that you can follow along and learn a lot about how to write these functions in a more efficient and effective way. Some of the considerations we should bear in mind are speed and efficiency, but also readability of the code and understanding of the algorithm, also the application of where the algorithm is going to be used. So for example, in the course that I'm producing, it's for a deck of cards. There's 52 cards in the deck, so there's not a lot of data there to be shuffled about. So the function that we use doesn't necessarily have to be amazingly performant because it's only shuffling 52 cards. So bearing that in mind, let's go to Xamarin Studio and start producing some of these functions now. I'm here in Xamarin Studio and I've created a project, an F# library, and I've called it Follow Along Benchmark Shuffling because I want it to be possible for you guys to follow along, and of course we're going to be writing some shuffling functions and benchmarking those functions. So the first thing I want to do is to add a file to this project. So I'm going to add a new file. It's going to be a source file, and this source file is going to be the source file that contains the function for shuffling some items in a list. It's going to be a generic function, and we're going to call it duplicate selector. The reason why I'm calling it duplicate selector is because the algorithm is actually quite a bad algorithm to use, because what we're doing is we're going to be randomly selecting a number, but we're not going to remove that number from the list once we've selected it. And then we're going to add that to another list, and what we're going to do is we're going to be in an iteration, and then we come back and we randomly select another number, but it's possible for us to select a number that we've already had before, so that's why I'm calling it duplicate selector. Let's create a module and give our module a namespace. We'll give it a namespace of FSharp.TV, and the module itself will be called dup selector. And dup selector is just going to be a basic function, and we'll call that one dup selector. And it's going to take in two parameters. Let's take in a list of items. And like I said, it's going to be generic. and we're going to give it a seed. We're going to have some semblance of a pure function. That is, it's going to be idempotent, which means that you put in a single value and you always get the same response back out again. So whatever same value you put in, you always get the same response or the same result. And in order to make this list shuffleable and randomly shuffleable, we'll have to have a random type. So I'm going to create a random number generator using the .NET system random, and we'll need to get the size of our list before we do anything at all. So we can get size, and that'll be the list of items, and we'll pipe that into list length. So the reason why we want the size is so that when we select our random index, we're going to create a random index to select from the list. We want to make sure that we're going to select an index that is not greater than the length of the list, otherwise we'll get an out of bounds exception. So now we've got our random generator and we've got the size that we want to limit ourselves to. Let's create a recursive function that will work its way through the list of items and turn it into a shuffled list. So let recursive called shuffler, and we're going to give it the shuffled parameter, and that's going to be our list that we're going to start building up. And we're going to say the count is the result of the shuffled length. So we're going to get the length of the shuffled list. So list.length. And then we're going to get the count, and we're going to check that count against the size, and if the count and size are equal, that means that we've finished shuffling the list. So we're not there yet because we're still writing the function, but this is the case when we've shuffled all of our items. At that point we can return out the resulting type, which is shuffled list. Otherwise, if we've not finished shuffling, let's get the next index, and like I said, we'll use the random number generator. So equals RNG and next, and then we make sure that we constrain it to the length of the list that is coming into this function. And this is also the point where we should draw some attention to the size here. It's always going to be the same because we've specified it outside of our recursive function. So if there are 100 items and we take off the 100th item on the first time around, we can randomly generate loads of indexes, and each of those randomly generated indexes could also be 100, and at that point we've already taken it off, so there's no point trying to take off the same one again. So this is why this particular algorithm is bad, because it's not reducing the length or the size here for the random number generation. So we always stay within the bounds, but also compacting the length of it as we go along to make sure that we don't search for unnecessary indexes and therefore having collisions with indexes that have already been pulled off. So we can say let item, and now we use the index that we've just got, and we'll say list of items, and we'll fish out based on that index the actual item that we want using a dot, not a comma. And now we've got that, we can then start to check to see if the shuffled list already contains that item. Because if it does contain the item, then we just return shuffled as part of the call to shuffler again. Otherwise, we know that we don't have that item in the shuffled list. So let's call shuffler, but let's cons that item to the front of the shuffled list. So that's what the idea of this recursive function is. That's to incrementally add each item that it finds via the random index generator here from within the list of items. So we need to make a call to the recursive function now to complete the implementation of the duplicate selector. So we can just say shuffler, and we'll pass in an empty list, which will be the empty shuffled list. So we've got this, we've got ourselves a function, there's no red underlines anywhere, but we want to start benchmarking this, so let's add a file to start benchmarking. So let's call it benchmark, and it will be a source file. Add that. In fact, let's change that to a script file. We don't need to have a source file, in fact. We'll just use that as a script file. And what we're going to do is we're going to load duplicate selector fs. So we've got that file loaded. Now we can open via the namespace, so FSharp.TV, and we'll take the duplicate selector. Now we've got the duplicate selector, let's create a function that we can start benchmarking with. So we've got the benchmark, and we'll call that one benchmark dupe selector. And as it's a shuffle, let's put the word shuffle there too. A nice long name, because you can tell I'm a C# developer, right? So duplicate selector is what we're going to have to call, and we're going to give it a list. So let's give it a list from 1 to, and we're going to take the size that we've passed in, so it's always going to be limited to that. And of course it needs a seed, so we'll just give it the integer of 1, and that is it actually. And we'll just give it an ignore because we don't want the results to be returned from this function. We just want to call it and benchmark it. And we can benchmark using the time directive, and then we can call the benchmark dupe selector shuffle, and we'll just give it 100 items to begin with. Now we've got this, let's compile the app, and then we can control and enter, and it says that it's taken 5 milliseconds for that to take place, or 6 depending on which one you look at, the real time or the CPU time. Okay, so let's increase the size of our call now. Let's increase it to 1,000 items, and let's see how long it takes for it to produce a result for that. So it's now taken 1/4 of a second, 232 milliseconds, and you can see that it's slowing down quite significantly. So I'm going to add another 500 items just so we can see the speed that this takes. Half a second. Let's try 2,500 just to put it through its paces. And now you can see it's taken well over a second. Okay, so that's one way of doing it. That's our duplicate selector. It's a very functional approach because we've got a seed that comes in, but we've not actually used that seed, which is what we should be using here in the random, because now we can ensure we always get the same result out whenever we call this function, and I'll show you that now. If we call duplicate selector just straight from here, in fact I'll need to specify the size. Set our size object to 100, and now when we highlight and execute, it says that duplicate selector is not created because we've got to run those lines in. Now those are there. Now we can highlight this, execute. 82, 46, 20 is the first 3, and it's always the same items every time, no matter how many times I call it. Now we've got a pure function because you're putting in the same items and getting the same result back out at the end. We'll ignore the fact that it's using system.random because I'm sure that probably negates the fact that it's a pure function by using that, because this uses mutation under the bonnet. So I'm going to ignore that and just assume that from my point of view as a user of this function, it looks to me as a functional function in terms of functional concepts, because I'm getting the same result out every time when I give it the same seed. So we've got ourselves one of those items here now benchmarked, and it all seems to be working nicely, and we know that when we run it, it takes a long time for all of the code to actually be executed. In fact, it takes almost 2 seconds now when we've got 2,500 items in it. Is there a way of speeding this up? Well, of course there is. The way that I'm going to show you to speed it up now is to create a mutable version of this. And I don't think the mutable version is actually that horrible looking, although there is a sort of a feeling that in order to get things performant, you end up making the code look ugly. But I don't think this one is actually. So this one we're going to say, I'm going to call it mutable duplicate selector. So mute duplicate selector, and we'll create a module for it. So module, and it will give an FSharp.TV namespace, and this one will be called mutable duplicate selector. And now we've done that, let's create the function for it. So let mute dupe selector, and we'll pass in an array of items, and we'll also give it a seed, and again we'll create ourselves a random number generator. So RNG equals system.random, and we're going to get the size of our array of items. So let size equals array of items, and if you'll note, in the first one I was creating a list. That's because it was a bit more usable for me to be able to just add an item using the cons operator. But here we're using an array of items because arrays are actually faster than lists, and we'll see later a clear indication of how that is so. Let's create ourselves a shuffled resize array. So this gives me a chance to test out the resize array type that the .NET framework gives us. So resize array, and it comes from the system collection generics type. It's a list, I believe, and it's quite a fast item, so it's useful for us. And what we're going to do is we're going to use a while loop, and we're going to say while the shuffled count is less than size, we'll continue iterating over the unshuffled and picking out an index and an item using that index. So we'll say let index, and we'll use our random number generator to get the next item, and we'll use the size to make sure that we don't go out of the bounds of that. And then we can say let item be the item that we take from the array of items using the indexer. And we can do an if expression now, and we're going to check to see if the shuffled already contains an item that matches the item we've got here. If it does, then we won't do anything, we'll just continue. But if it doesn't have the item, then we're going to add it to the shuffled. But what we need to do now is copy all of the items in the shuffled using the copy to, and we're going to copy that into the array that we've passed in. So now we've updated our array. Let's close the FSI, and that looks fine. There's no underlines anywhere. Let's go to the benchmark file. Let's add the file for this one now. So we load that one up too, and that's mut duplicate selector fs. Let's rename this file so that it's got the correct name. And now the underline has disappeared, and we can open the FSharp.TV namespace for that mutable selector. Let's copy this line, paste there, and what we're going to do is we're going to say benchmark the mutable duplicate selector. And so mutable duplicate selector, and note that it has an underline because it takes in an array now, not a list. And now let's compare the two. So I'm going to put that underneath it, and we need to call mut dup selector shuffle. And now if we highlight everything, executing the FSharp interactive and fixing the errors that we find, error FS222 files and libraries must begin with a namespace module declaration. Is that because I've got to compile? Let's try again. Okay. And let's highlight and execute again and see if that's fixed it. Timing is now on, and you can see that this second one is about 8 times ish quicker than the first one. So we've automatically, just by adding some mutability, made one of these implementation faster than the other one. So that's how mutability and functional programming are sort of working in different ways. So the mutability enables you to go faster, and you have less items on the GC stack as well. So let's go back and see if we can improve this somehow, but in a functional approach. So let's add another algorithm, and this algorithm is going to be a derivative of the Fisher-Yates algorithm. So the Fisher-Yates, if you've ever heard of that, is an algorithm that was devised in the 1930s. And you can find information about it if you go to Wikipedia. There's loads of information about it. It's a well-known algorithm. Although when I first started doing the project, I didn't know very much about it at all. But the great thing about FSharp is that I'd automatically been steered towards it by the language because it just seemed obvious to me. And the language of FSharp enabled me to implement that quite easily. So let me show you how the Fisher-Yates algorithm looks. Let's start by adding a module, and of course with the FSharp.TV namespace. So FSharp.TV, and this one we're going to call Fisher-Yates. And we're going to create a function called Fisher-Yates. And the function will take in a list this time. So we'll take a list of items. I want this one to be a functional approach, and we'll pass in our seed. And I just want to double check to make sure that I've passed in my seed to my random generator, otherwise it's not going to be able to generate the same results every time. And now we create ourselves another random number generator in our Fisher-Yates algorithm using the system random again. And we're passing our seed. And the approach we're going to take now is going to be similar to the one that we did in the duplicate selector, and we'll use a recursive function internally. However, this time we're going to take in two parameters. So we're going to say let recursive function shuffler, and we're going to take in unshuffled and shuffled. If you've been following along in the course, you'll recognize this by now. And we can say let count equals unshuffled list.length. So now this gives us the length of the unshuffled list that we've got coming in. And what we want to do is we want to make sure that the count which we've just created is equal to 0. Then we know that we finished and all of the items are shuffled. So we can say if that is the case, then just return out the shuffled list of items because we're finished with it. Else, let's continue working through and shuffling them all. So we'll create a new index, the same as we have in the previous ones. But this time we're going to do something different. We're going to get the count now of the unshuffled, and we're going to make sure that we capture the random number that only goes up to the count. So every time we go through our recursion steps, we're going to decrement the count until it gets to 0. So we're compacting the range of numbers that a random index is obtainable from. So now we can get our item, and we'll get the matching item from inside the unshuffled list, and we'll take the index again as we have on the previous ones. And this is where it becomes a bit more interesting, because we're going to have to use a function to create a new unshuffled. So new unshuffled is the result of the unshuffled being filtered. So we use a list.filter, and that is a function that takes in the item and it compares the item to the one that we've retrieved using the index, and if they're not the same, then we don't include it in the filter. And now we can get ourselves a new shuffled as well. So we're going to update shuffled with the new item, and note that we don't have any if expressions happening here. We're just taking the item directly from the item that we've indexed, and then we can just call shuffler with our new unshuffled and our new shuffled. It's as simple as that. Now we've got ourselves a function that we should be able to call, and it will return to us a shuffled list. So we've got ourselves the third algorithm. Let's have a look at the benchmark now. Let's compile our code just so we know that that's ready and waiting for us to use. Let's load up the Fisher-Yates. So load, and it's Fisher-Yates.fs. And let's open the namespace for that and get the module. So FSharp.TV Fisher-Yates. Let's copy this benchmarker, and we'll change that from this to Fisher-Yates Shuffle. And note that it's a list we're feeding in, not an array. And it's just Fisher-Yates. Let's duplicate the last item. Benchmark Fisher-Yates Shuffle. And let's highlight everything, execute in the FSharp Interactive, and we should see how fast each of these are. And as you can see, we've got ourselves the mutable version, which is still faster than the Fisher-Yates one that we've just created. It's about half the time that the Fisher-Yates takes, but the Fisher-Yates is a second and a half faster than the functional approach using the duplicate selector. But of course we can turn it into a mutable version. So let's do that. So I'm going to add another algorithm, another file to put that algorithm into. And this one we'll call the mutable Fisher-Yates. Let's create a module, and that module will be called FSharp.TV. I'm guessing you get the picture now. And we're going to create ourselves a function which will be called Fisher-Yates, but a mutable version of it. And we're going to pass in an array of items now, and the seed, We'll create our random number generator using system.random again, and we're going to get the size as we've done before, and the array of items into array.length. So we've got a length of the array that we're passing in, and we get our shuffled now. And our shuffled, we're going to create a resize array again, and our unshuffled is going to be a resize array also. And the reason why we're doing this is so that we can take our array of items into the resize array and use that as we go along. Let me just reset this and close the window. We're going to create another while loop, and we're going to check the shuffled count is less than size, because if it's less than the size, then we still need to shuffle the rest of the items. So we can then say do. We get the index as we've done before using the random number generator, and this time we're going to use the unshuffled count so we can compact the range of numbers that we go over every time. And then we get our item from the unshuffled, making sure I put the equals symbol in, and we use the index for that. Now we've got our item, we can then remove that item from the unshuffled because we don't need it anymore. So we take the unshuffled, move the item from there, and then we can pipe that into ignore because I don't really care about the Boolean result. And then we can say shuffled.add, and we put the item that we've already fished out onto that. And now we should have a complete function, and we should be ready to go. Use that to shuffled, make sure we've got the right names. And then we can say shuffled.copy to, and we're going to copy to our array of items. And now our function should be ready to use again. So let's save, compile, add it into the benchmark again, and now we open the namespace and access the module. Let's add another step here, and we're going to benchmark the mutable version of it and pass in an array. And now let's highlight everything and execute in the FSharp interactive and catch any errors if there are any, but they're not, so that's good. And now we can see that our mutable version is now super fast at just 5 milliseconds, so we're happy with that. However, I just want to change the way we do our benchmarking. I'm going to reset this, close this window, and I'm going to delete all of these because I want to put in here some code that I've already written, which gives me a bit more information. So what I'm going to do is I'm going to create a series of sizes, and these sizes are the sizes that can go into each of these functions. Now for some of these I don't want to go too high because it might take an extremely long amount of time for them to finish. So I'm going to put some limits on them. So we've done our Fisher Yates, we've done our mutable duplicate selector. So let's start plugging some of those ones in there now. So if size is less than 20,000, I think we're safe to say that we can let the mutable duplicate selector run. So in fact, let me just add in another function. I've taken a function that Scott Voloshin has given me, and we're going to use that function now to generate the timings and the memory usage. So it's the function here called time. It takes in the number of iterations that we want to run a function that we're going to provide it, and we're going to label that function so we know which function it is that has been executed. We just gather some information from the garbage collector about which generations are in use, how much memory has been used, and we're going to use a stopwatch to measure how long it's taken for the function that we're calling to be executed and complete. So that's how this function is working. So we can call our time function. I'm going to call it 5 times, and we're going to give it a label. I'll create the label in a second, but the the final parameter that we need to give it is a function, and the function will take in a unit and it's going to call one of our benchmark functions. So we're going to benchmark the first one, which is the duplicate selector shuffle, and we're going to pass it the size that comes in there. So now let's create our label. So let label, and that label is just going to be a sprintf, which will be the name of the function. So we'll take the name of the function here, and we'll just say %i, because we're going to get the size that it's tried to execute at. So it's going to be one of these items in this list here as we go through our iterations. So that's how we did a duplicate selector, and that's how we're going to measure it. So we're going to say for this one, in fact I'm going to reduce this one because this one's actually quite a terrible function to do. So I'm going to say 2000 only. No, I'll let it go 5000. And now let's highlight it all, execute in the F# interactive. Let's see what the output is. Okay, so it's iterating through them all, and it's doing it 5 times for each one, and it's gone up to the limit, and we can see that for 1000 records it's taking approximately 200-ish, 210, and for the 2000 records it's pretty much 4 times slower. So just by doubling the amount of records it's taking 4 times as long, and you can see that in the generation 0 there's 106 items in that collection. So there's like 4 times the items, so it's taking 4 times as long for it to clear. So we've got ourselves a new time function that we can use instead of the old-fashioned time. Let's plug in the other bits of information that we had, which were the duplicate selector and the mutable one. And let's update them so that we're using the different benchmarks. So we want the mutable duplicate selector. So let's update that. And we want let's move that one down, in fact. And we want the Fisher-Yates. And finally let's put in the mutable version as well. So we've got the mutable version also to compare. And the mutable version should take a lot more records easier than the original 3 that we've started off with. So the mutable Fisher-Yates for 2000 records is only taking 3 milliseconds. However, the original Fisher-Yates is 197 milliseconds, so you can see a massive difference in that already. So we've got some data here that we can look at if we need to. But let's continue. So we've got ourselves different implementations now working. You'll notice that for each of the implementations I've used different types. So for here I've used a list, and for this one I've used an array. And we know that arrays and lists are different structures and the arrays are usually faster, but we've not actually proved that. But by the end of the video I'll show you that it is actually the case. But let's continue now and let's add yet another algorithm. This algorithm is an algorithm that I got from one of my advisors, and it's an extremely efficient way of doing a shuffle, although it seems a bit counterintuitive because I'll show you why. But we're essentially using an algorithm within the .NET framework to sort data, but we're using the sort to shuffle information. So this one was actually a code golf exercise, and it's a very interesting use of the .NET framework. And we're going to say let code golf, and we're going to pass in an array of items, but we're going to help the type inference because otherwise it will have difficulties trying to figure it out. And it's going to be an array, as I said. We're going to pass in the seed. So now let's create ourselves another random number generator. It's getting a bit repetitive now, isn't it? And now what we're going to do is we're going to create some keys to sort by. The keys we'll create using expression, and we'll convert that expression into an array. And what we're going to do is we're going to look for every item in the array of items. I don't really care which item I'm at because I'm not even going to use that item. I'm just going to randomly generate a number. Any old number will do, doesn't matter how big it is. And that is going to be our set of keys, and I need to put the equal symbol after key. Now we've got our set of keys. This is where the interesting use of the array sort method happens on the .NET framework. We use our keys as the list of numbers to sort against, and then we pass in our array of items, and that's our sort function complete. And let's add this to our benchmark FSX. So we can do that by saving the file, compiling the solution, make sure there's no errors. If there are, we'll fix those. And let's load that file. Now we've got our code golf function available and ready to use. Let's create a benchmark function for this one. And it's going to take in an array, because that's the type it requires. And then we'll add another version of the call here. I'm not going to put any limitations on this one because this one is definitely going to be able to cope with what it's going to be fed. So it should be fine for this one. So let's copy over that and put that over the label, and let's highlight everything, executing the F# interactive, and we can see the result of all of these being used. So the code golf is quite fast. It's so fast it's almost not registering. Even whilst it's trying to shuffle 1 million records, it's doing it still in less than half a second. And when we multiply that by 10, you see that the factor it goes up by is a order of 10 too. So it's not exponential as it's increasing, which is quite cool. It's quite good. However, in my investigations, I decided to find out if I could go one better than the code golf. And as a rather competitive person, I managed to find a way of doing the same thing in a shorter or fewer amount of lines. This one we're just going to call short, and the short function will take in a list of items, and it will take in a seed, and we'll create our random number generator in the same fashion as we've done for the past items. And then we've got our random number generator, and because I like things to be short, I'm just going to say list of items, and we'll pipe that into list.sort by, and this is where the magic occurs because we don't even care about the item. We're just going to do something similar to the last one, where we just get the next item and allow the framework to do its magic. So save that, compile it, make sure that's all fine. And so with essentially 3 lines of code, we've managed to do the same thing. And let's benchmark this, and this is going to be called the short. So benchmark short shuffle, and let's add that and make sure that we load it. Okay, so that all looks sweet. Let's get rid of that, make sure that that's a list, and now let's add also benchmarking for that item. And so this is going to be a short label, and we're going to benchmark the short shuffle, and let's highlight, execute and fix any errors. There are no errors, so that's good. And we can see from that line there that the short shuffle and the code golf are pretty much even at the moment. So there's not much to separate them. Now there is something noticeable. So the code golf is actually a lot more efficient. So the advisor that gave me that should be quite pleased with that. I tried to outdo him, but I couldn't quite do it. So we've got 10 million records now that we're testing against the code golf, and it's slowly getting through them, and now my shorter version is now attempting to go through them all, but it's a good 2 seconds slower, unfortunately. So I tried to beat it, but I couldn't. However, let's wait for this to finish. Some of you may have already noticed what I could do to change it, and I'm going to actually go ahead and change it. So there we go. It's on average about 6 seconds, whereas this one here is about 4 seconds, so there's about 2 seconds difference. However, what I'm going to do is I'm just going to change it, because I first of all started with a list, but why don't we just be cheeky and use an array, and we can also see the difference between using an array and using a list. So I'm now actually going to call that an array of items, because I'm going to treat it as an array. And that doesn't seem to have caused a problem, so that looks fine. Let's go back, and that's underline has now disappeared. Let's highlight everything, execute in the F# interactive, and let's wait for the 10 million rows to come up, and we can highlight those and see what it looks like. So there we go. Now the quick versions are now doing their business. So now we're on to 1 million records. Now 10 million records for the code golf, but we can already see that my short version has now managed to just about edge the code golf version. So it's averaging about 4 seconds at the moment for the code golf on the 10 million records. The short shuffle that I've created now manages to shave off yet another half second on top of that. And note that the items that are ready for garbage collection on Gen 1 and Gen 2 are actually higher than on the short shuffle. You can also see the amount of memory that it's clearing up when it does here, where it's done an integer wraparound. It's doing a garbage collection there, and that will slow things down somewhat too. So we've managed to benchmark all of these different algorithms, and we've come across a few things as we've done that. So we saw at the end that the array is actually faster than the list. So to recap, we wrote 6 functions in all. They all had qualities about them that were different from each other, such as the duplicate selectors. They didn't filter out any of the items and compact the number of items they could generate an index from. So that meant that the algorithm performed quite slow. We had a functional version of the Yates that was also used, and that seemed to add some element of speed compared to the duplicate selectors. However, the mutability side of things gave a performance boost, a massive performance boost, even compared to the Yates when you filtered out items, so you didn't have to check for those again. The quick sort with the code golf example is an in-place sort, so it's sorting it inside the array, and it's using a lot of mutability under the hood to perform the magic that it's doing. And it's the same for the sort by that I'm using in the F# code. That's enabled us to create some rather fast and short code. However, using the method called sort to do a shuffle seems a little bit counterintuitive, although it does work, and it's actually a brilliant use case for using the sort. And in fact, I guess it's intended to be used that way, otherwise they wouldn't give you the keys property for the first parameter of that function. If you want to find the code for this and correct it, make it better, and do your own versions of it, the source code is available at github.com/FSharp.TV, and you can just look for it on the code alongs or the follow alongs repository. Thank you for watching. Stay in touch at FSharp.TV. My name is Mark Gray, and I hope to see you in another video in the future.